Hi, my name is Silvana Aristizabal, and this is my lab report for Lab 2 on projectile motion. Here's a table of contents of what we're going through in this presentation. Firstly, the introduction. The overall purpose of this assignment is to observe, analyze, and model the motion of a projectile. We will achieve this using three main tools: Tracker for video analysis, Glow Script for building the computational models, one only accounting gravity and the other accounting gravity and drag force, and lastly, spreadsheets for comparing the observed trajectory of the object with the two predicted trajectories. All of this helps us gain a deeper understanding on Newton's second law of motion and the effect of drag force. Let's explore more. So Newton's second law of motion states that the net force acting on an object is equal to the rate of change of its momentum over time. In other words, when a force is applied to an object, it changes its momentum, which is the product of its mass and velocity. We can see here how by deriving from the momentum principle, we can obtain the velocity update formula. This formula allows us to determine the object's velocity at each time step when dealing with a non-constant force. Once we have the updated velocity, we can use the position update formula to predict the object's future position over time. The drag force is a resistive force that opposes motion through a fluid, such as air or water. It increases with speed and always acts on opposite direction of motion. The equation for drag force is this one. V is a proportionality constant, V is the velocity, and V hat is the unit vector indicating direction. This force is crucial in modeling the real-world motion, like falling objects and projectiles with air resistance. For our procedure, we first recorded a video of a crumpled up paper falling off a table and uploaded it to Tracker to record position at each timestamp. Then, based on the position, velocity, and time gathered from the video analysis, we created a computational model of the ball's position on Glow Script, first accounting only gravity and then also accounting air resistance. Then we graph the Y position versus X position results from the computational models and the video analysis to compare results and understand the difference between data and discuss findings. Now let's take a look at the actual data we analyze. Here's a video of the ball being thrown off the table, which we use for video tracking. By examining its motion frame by frame, we collected trajectory data. More clearly, our system, the crumpled up paper, is influenced by its surroundings, including air resistance, gravity, etc. With the data we collected, we were then able to construct a computational model of the motion we observed. So from Tracker, we know the starting and final time and position. With this, we were able to calculate the velocity using this formula. We were also able to find the change in time here. With all of this information, we were able to plug in the mass that we had calculated, the initial position, the calculated velocity, the initial time, the change in time, and then final time and the drag force. For the computational model that only accounts for gravity, we used a zero drag force. And then for the next model that accounts also drag force, we included a B proportionality constant. Then we also applied Newton's second law and calculated the net force using the force of gravity and the force of drag. Then we also adjusted the vectors to show the direction of the forces. By running this code, we get two series of numbers, one that accounts only for gravity in the object's trajectory and the other accounts for both gravity and drag force. If we graph these computational results side by side with the actual observed results from the video analysis, we can obtain a graph that looks somewhat like this. As we can see, the green dots represent the computational model results only accounting for gravity, the purple accounting both gravity and air resistance, and the blue dots represent the video analysis trajectory. As we can see, the blue dots take a curvature, which represents the real-world environmental factors that were actually affecting the crumpled up paper. The green data, which only accounts for gravity, is a straight line given the small mass of the paper. Because of this, gravity did not have much effect on its trajectory. Then, the purple dots are meant to represent the closest model to the observed trajectory of the ball, as it accounts for both drag and gravity. Like the observed results, it also takes a curvature. However, the interval where the trajectory goes straight down can be due to an error in the code or the B constant that I utilized. Now let's take a look at the possible sources of error in our experiment and how they might have affected our results. So for the human error when conducting the video analysis, rounding errors could have affected our calculation. The camera misalignment when recording the initial video and dismissing other environmental factors could have all affected the results of. So now to reflect on the overall experiment, we can answer a few questions. Do any of the models predict the terminal velocity? If not, what similar experiment could you design to find the terminal velocity of your object? So for the model that only accounts for gravity, the object speed continues to increase indefinitely, meaning it does not predict a terminal velocity. For the model accounting gravity and drag force, the object experiences a nonlinear velocity, which suggests that the existence of a terminal velocity. So for our final question, would the object take the same time to reach the ground if it were thrown straight up with the same initial speed as in the experiment? Throwing the object in this motion would actually increase the time it takes to reach the ground because we have to account for the time it takes to reach the maximum height and then the time that from the maximum height to the floor. We also have to account for the vertical and horizontal motion separately. In the original experiment, part of the initial speed goes into the horizontal motion. In the straight up throw, all the initial speed is in the vertical direction, meaning a longer rise and fall time. Thank you.